All right, welcome back. We're going to continue with examples of finding points of inflection. We did this one, x to the power of 5, and I invite you to try on your own x to the power of 4. And you'll find that there's no point of inflection there. It's concave up on both sides of the point that could potentially host an inflection point. It would be x is equal to 0 again, but it's always going to be concave up. Here's a more typical type of problem that you'll see on, potentially see on an exam or a quiz. Find where points of inflection occur for the function f of x, 1 over x squared plus 3. And there's a hint. The hint is, here's the second derivative in a beautiful, almost fully simplified form. So what this question is doing is it's not testing your ability to find f prime and f double prime. It says, no, I don't want to test that. I'm going to test that somewhere else. I'm going to give you the second derivative and say, do you know what to do with it? So if you're asking for points of inflection and only given the second derivative, that's a pretty big hint that it has something to do with the second derivative. We're going to go through the recipe, starting at step 2. Step 1, take the derivative. Step 2, now we're going to set f double prime of x equals 0 and f double prime of x dne. Okay, so f double prime of x is equal to 0. That means 6 times x squared minus 1 over x squared plus 3 cubed is equal to 0. I'm going to cross multiply and I'll get 6 times x squared minus 1 is equal to 0. So 6 times x minus 1 times x plus 1 is equal to 0. That's a difference of squares. I can factor it. We get two solutions. We get either x minus 1 is equal to 0, so x is equal to 1, or x plus 1 is 0, so x is equal to negative 1. I'm going to do the other one now, f double prime of x dne. How do we handle that? So this means bottom equals 0. And that means x squared plus 3 cubed is equal to 0. That thing's only going to be 0 if what's inside the brackets is 0. So that means x squared plus 3 is equal to 0. Equivalently, you can say I'm going to take the cube root of both sides. And this is impossible. X squared is always positive. We're adding 3 to it. This cannot be 0. Since x squared is always positive. For any real number that we plug into this, x squared will be positive. So we're taking a positive number plus 3 and saying, what positive number plus 3 gives you 0? There is no positive number that does that. Okay, so we only get two numbers to put on a number line. Going from minus infinity to infinity. Cutting the number line at those two test values, at negative 1, positive 1. And now we have 3 test regions, so we need 3 test values. I'm going to pick negative 3. Now I need a number between negative 1 and 0. Oh, sorry, negative 1 and 1. You can pick a half if you want, or a third, or negative 1/3, or 0. If you want a nice number, pick 0. And then number from 1 to infinity, I'm going to pick 6. Those are my test values. Okay, then we're going to plug them into the second derivative. F double prime at negative 3 is 6 times 9 minus 1 over 9 plus 3 cubed, which is going to be positive times positive divided by positive, positive times positive divided by positive, so we're going to get something positive there. That means it's concave up in the first region. from negative infinity to negative 1. Now we're going to plug in the test value in the middle. F double prime of 0 is 6 times 0 minus 1 divided by 0 plus 3 cubed. That's going to be positive times negative divided by positive, so that'll be negative. So it's concave down in the next region. And then f double prime of x at 6 is 6 times 36 minus 1 over 36 plus 3 cubed. Please don't multiply that out, 39 to the power of 3. It's pointless. All we care about, we have a positive times a positive divided by a positive, so we're going to get a positive. And that again means concave up in that third region. Okay, now what does that mean? Okay, I pulled a sneaky and just paused and shrunk the text down a little bit to fit some more stuff underneath. So what does this mean in terms of points of inflection? Well, it means I forgot to draw the last concave up picture. But what does it mean otherwise? Well, we have a change in concavity across x equals negative 1. So we have point of inflection there, POI, at x equals negative 1. Y equals f of negative 1, which is 1 over 1 squared, or negative 1 squared, so 1 plus 3, so 1 over 4, and POI at x is equal to 1, y equals f of 1, which is 1 over 1 plus 3, 1 over 4. So I'll just summarize all that. We have a POI, two points of intersection. One of them is at negative 1 comma 1 over 4 and positive 1 comma 1 over 4. I'll quickly show you what that looks like. Okay, so we have 1 divided by x squared plus 3. Looks like nothing unless you zoom in. There's the zoom in. And what we've identified is that there's an inflection point at negative 0.25. So right there, right at that point. It's hard to see. It's hard to tell that it's concave down in this region. Unless I shrink down the axis, maybe that'll help. So I'm going to go from negative 1 to 1. The x-axis and the y-axis, I'm going to go from 0 to 0.5. I'm going to zoom out a little bit. Okay, it's still very hard to tell, but it's concave down from negative 0.25, so from there to there, then it switches to concave up. It's very subtle to tell by looking at the graph where that inflection point is. So to recap, what we've done so far with the second derivative is we've used it to locate locations where the function is concave up and concave down, and then in turn we use that information to define these new points called inflection points that have these very important properties in analysis of functions and analysis of data. The second derivative doesn't stop there in terms of the information we can extract from it. I would, if you've been going through this set of videos right now, I would take a break, take a pause, have a snack, do something else, come back, because this is different. And if it's good to treat this as a completely new type of thing. Yes, we're going to use the second derivative, but it is easily confused with what we've already done. So just pretend that you've taken a break, got some cheese and crackers or something, you had something to eat, maybe took a walk. What What we're going to do next is called the second derivative test, which is not what we've already been doing. What we've already been doing doesn't really have a formal name. Some people call it the concavity test. Some people unfortunately call it the second derivative test, but they are very, very wrong. I'm gonna call it the concavity test, the thing that we just went through, using the second derivative to see where a function is concave up and concave down. The second derivative test is not that, it's something different. So I'm actually not gonna call anything the second derivative test. I'm gonna call this this next thing we're gonna do, I'm gonna call it the combo test. You'll see why. So in addition to telling us where a function is concave up and concave down, the second derivative can also be used to diagnose critical points. So I'll explain what I mean. To get a critical point, you set the first derivative equal to 0, solve for x, and then what we have been doing up until now is we've been making a number line, choosing test values, plugging test values into the first derivative, checking if the derivative is positive or negative, and then making these arrow diagrams to see where the function is increasing and decreasing, and then interpreting that to mean whether or not a certain critical point is a max or a min. There is a shortcut. Look at this graph with all the max and min on it. Notice that every location where there's a max, the graph is concave down. Every location where there's a min, the graph is concave up. This is a little bit misleading because it isn't always this case for every single type of function. Some functions have this format. There's a max and it's concave up on both sides. Or it might be a min where it's concave down on both sides. Those max and min, the ones I just drew that aren't on this picture, they come from the first derivative not existing. The method I'm going to show you is not applicable for those types of max and min. It's only applicable for max and min that come from the first derivative being equal to 0. And it is a beautiful shortcut. Okay, so just to warn you and to use the vocabulary that I'm going to use for the course, the second derivative can be used in two different ways to extract information about the function f of x. We can use it to extract information about concavity, and we can use it to extract information about max and min. For the second one, we haven't done that yet. I'm about to show you some examples of how it works. The basic idea is that we still need the first derivative to find the critical points. We set f prime of x equal to 0 and solve for x. But next, we do not make a number line. We do not choose test values. What we do instead is we go back to f prime, find the derivative of that, so find f double prime, and then take the x values that we got in the first step, plug those directly into f double prime, and see if the function's concave up or concave down at those x values. Because if it's concave down, we have a max. If it's concave up, we have a min, and that's it. It's super fast, especially if the question gives you the second derivative for free as a hint. So here's the recipe for the, oh no, I did it. Oh, I forgot to change it here. Second derivative test, combo test. Combo test. I like the name combo test because no one else calls it the combo test, but they should. And the reason they should is it's a combination of the first derivative and the second derivative. The first derivative tells you the points you have to explore for local max and local min, and the second derivative tells you what those points are. Now, this method has some flaws. I'll explain how it works, and I'll tell you what the flaws are. It works by finding f prime and f double prime, so you're going to need both derivatives eventually. You're going to find locations where the first derivative is equal to 0. So you're going to get those x values. Then you're not going to look for the x. If you're using the combo test, don't look for the values of x that make the first derivative not exist. The analysis can't use them. It's not powerful enough to test those values. Only the increasing decreasing test or first derivative test, if you want to use that name, only the increasing decreasing test can determine what those critical points indicate. Anyways, so once you find the critical points, you plug them into f double prime. If f double prime is negative, it means the function's concave down at that critical point. And concave down looks like that, which means a max. If you plug it in and get something positive in the second derivative, Second derivative positive means the function has this shape, concave up, which indicates location of a min down there. Here's one of the, so we've seen one flaw already, that this test cannot be used to diagnose critical points that come from f prime of x dne, does not exist. Here's the second weakness. What happens if you plug the number in, f double prime, the critical number in f double prime, and what comes out isn't positive, and it isn't negative, but instead it's that number in between, it's 0. That means the combo test has failed, that we can't determine what's happening for that number, if it's a max or a min. We would be forced to go back to the increasing decreasing test and make the number line choose a test value to the left and to the right. So two weaknesses. It can fail, and it misses all max and min that are sharp corners. So anything that looks like a corner or an elbow, any of those locations where f prime of x is undefined, it completely misses those. It can't be used for them. Let's quickly do an example. Using the second derivative test, determine the relative extrema of the function. So you have to unpack the sentence. Second derivative test. I will not write that. I will write combo test on the exam. And in brackets, I'll put second derivative test, but combo test is the preferred name for this course, because it's clearer. Determine the relative extrema of the function. Relative extrema means max and min. So I'll add that as a label. Max and min. So let's do the first part. We're going to take the first derivative, 3x squared minus 6x minus 24. We're going to set the first derivative equal to 0. That means we have to factor on a common factor first. So 3x squared minus 2x minus 8. This is a quadratic. I'm going to start product and sum method and see if that works. I want mystery numbers and those brackets to multiply to give -8, add to give -2. So -4 and +2 will certainly work. That means we get two x values. We get x is equal to 4, and we get x is equal to -2. Next, that's the first part of the combo. That's the f prime part of the combo. Now we're going to do the f double prime part of the combo. So f double prime of x is 6x minus 6, which is 6 times, well, I'm not going to do that because we're not setting this equal to 0. Now, evaluate f double prime of x at our critical points, which I didn't label. I'll label them now. These are the critical points or critical numbers. So f double prime at 4, we have 6 times 4 minus 6, which is positive. So f of x is concave up at x equals 4. So x equals 4 is a local min, since concave up looks like this, has that shape in the vicinity of a critical point. That's going to be a local min. Now we need the y value. Y equals f of 4. Oh, and this is where the regret for this function seeps in. F of 4, 4 to the 3 minus 3 times 4 to the 2. I'm going to screw this up. Minus 24 times 4 plus 32. So 64 minus 48 minus another 48. No, minus 96. Oh my goodness. Plus 32. What is this? Let's add the first two, or the last numbers. We got a 64 plus a 32, so 96 minus 48 minus 96. So those 96s cancel, so negative 48. Okay, now we have to check the second one. So this is a local min at 4, negative 48. Now we choose the second test, not test value, critical number, f double prime at negative 2. That's going to be 6 times negative 2 minus 6. So negative 12 minus 6, negative 18. But all that matters is that it's negative. Now we're going to plug that into the function. Y equals f of negative 2. So negative 2 cubed, negative 8, minus 12 plus 48 plus 32. So we'll get negative 20 plus 48. So 28 plus 32. That's 60. I think it's 60. You can yell at me if I'm wrong. It's okay. I can't add or subtract. It's one of my weaknesses. There's a local... Oh, and I forgot to say what it is. So I got to put the labels here. So a second derivative being positive means it's a min. Second derivative being negative means it's a max. Negative means concave down. The vicinity of a critical point. So that's what a maximum looks like. So local max at negative 2, 60. All right, and what does it look like? So I just pulled up a graph of that function. There it is. We found that there is a max at negative 2, 60, local max, and a local min at 4, negative 48, without making a number line, without choosing test values. Okay, and we'll continue in the next video.